So I'll wait for 2 to 3 minutes. Some more people are joining with us. Okay. So after 2 to 3 minutes, we'll be starting. Yeah, he is well. He is well now. So today class is up to 9:30. Class up to 9:30. 9:25 I will take 9:25. From 9:25 to till the end of the session, we will be continuing with the doubts. Okay. I will be allotting 1 more hour also, maybe in the phone conversation and all, or in Telegram doubts. 1 more hour from this day onwards. Okay. Other than this class doubts, we will be allotting 1 more hour in Telegram. Yeah. Good morning, Tonanda. Good morning. So kindly confirm audio, video, and screen once. Kindly confirm audio, video, and screen. So I think it's clear. So let's continue. Let's continue. See, actually, in the previous class, we have written LA equals to LB equals to LC equal to this equation. So called point to ln of GMD by GMR. So let me copy this. So this is that LA equals to LB equals to LC. I'm moving to the next slide. So just I want to write some sort of conclusion here. Conclusion, that's it. Just have a look. I can say LA equals to LB equals to LC, which you can call as L per phase also. That you can say simply inductance per phase also, L per phase. That is point ln of GMD by GMR millihenry by kilometer. What is GMD? GMD is nothing but simply we say cube root of DAB, DBC, DCA. Right? Distance between AB conductors, distance between BC conductors, and then distance between CA conductors. And what is GMR? We said, as we are thinking about only solid conductor, it will be 0.7788 into radius of the conductor. Okay. So I am asking you one very simple question here. Simple question. When this whole group is valid, when this is valid, when I can use this one? When I can say LA equals to LB equals to LC. Tell me please. When I can say LA equals to LB equals to LC. For symmetrical spacing, can I use this? For symmetrical spacing, can I use this one? Yes or no? Yes. For symmetrical spacing, we can use it safely. For unsymmetrical also we can use, provided that it is transposed. Means this is valid for symmetrical spacing configuration. Symmetrical spacing configuration. Or unsymmetrical transposed system. Unsymmetrical transposed system. Unsymmetrical transposed system. Provided that conductors are carrying balanced currents. This is one of the conditions what we have to maintain here. Okay. So provided that the conductors are carrying balanced currents. Okay, so then only this condition will be valid. Yeah, so I think voice is okay. Yeah, please kindly complete this one. I will be moving to a small problem. Thereafter, we will move on to some more discussion. So I am taking in the next slide. Yeah. So just have a look at this one. Consider the following three-phase system. Okay, so I am showing this is a conductor A and it's a conductor B, and it was conductor C. I will show. Conductor C. A to B distance, I am saying 8 meters. B to C, I am saying it is 7 meters. Already he said it's a three-phase system. First one is radius of each conductor. I will write. Radius of each conductor R is equals to 2 centimeters. Radius of each conductor is 2 centimeters. Yeah, first part. Find GMD and GMR of each phase. GMD and GMR of each phase without transposition. Without transposition. Very simple question it is. Simple question. Second one. Find GMD and GMR of each phase. GMD and GMR of each phase after doing transposition. After doing transposition. After doing transposition, we have to find out GMD and GMR. Okay. Kindly go through it. Kindly go through this one. Simple GMD and GMR calculations we are asking first without doing transposition. See, actually, without doing transposition, if you want to take up the GMD of phase A, GMD of phase A, what you should take? Distance between AB conductors and distance between AC conductors geometrically. So it will be DAB, DAC under root. Okay. What is GMD of B? B to A, B to C geometrically. What is GMD of C? C to B and C to A geometrically. That's it. What about GMR of phase A? R dash, phase B, R dash, phase C, also R dash. Because all the conductors are having identical in size. So GMR value depends upon only size of the conductor. GMR value depends upon only radius of the conductor. That is 0.7788 into radius. If it is a solid conductor, moreover, we have only one conductor in each phase. Moreover, we have only one conductor in each and every phase. Okay? Yeah. So let me write in the next slide. In the solution. Solution. First case. Untransposed. Untransposed. Okay. So GMD of the phase A is nothing but root of distance between AB conductors and distance between AC. Distance between AC or distance between CA, both will be same. A to C, C to A will be same. Okay. What is that AB distance we have? 8. Okay. Next, what is that AC distance we have? 8 plus 7. So it will be 15. 15. So it will come in meters. Next. GMD of the phase B, if you are thinking, square root of DBC into DAB or DBA. DAB or DBA. Any letter we can use, both ways. DBA. So it is square root of, what is the DBC distance? BC 7, BA 8. So it will be 7 into 8 under root. Next, phase C GMD will be square root of C to A, C to B. C to A, C to B. C to B. So what is that C to A distance you have? C to A, it is 8 plus 7. So it will be 15. And then C to B, it is 7. Okay, just check these numbers quickly. What will happen to these numbers? And moreover, you know, GMR of phase A conductor, phase B conductor, phase C conductor, all the three are exactly equal, which is 0.7788 into radius. Radius of conductor is 2 centimeters. So 0.7788 into 2 centimeters. 2 centimeters. Okay, yeah. First number how much? First number anybody? Tell me the sequence, all the three. 10.95 first number. 95. Second number it is 7.48. Next number it is 10.24 meters. Meters. And how much is GMR in centimeters? GMR 1.556 centimeters. 1.556 centimeters. Here. So it is for untransposed case. Untransposed case. Next, if it is transposed, what you should say? Anybody please tell me. If it is transposed, what we should say? GMD. How the 3 GMDs we have after doing transposition? After doing transposition, how will be the 3 GMDs? All the 3 will be equal, na? All the three will be equal. Equal to what? Cube root of DAB, DBC, DCA. That's it. Okay. Irrespective whether it is a horizontal spacing, vertical spacing, doesn't matter. After doing transposed case, the transposed case, GMD of all the three phases will be equal. GMDs of all the three phases will be equal to cube root of distance between AV conductors, distance between BC conductors, distance between CA conductors. So it will come to be cube root of what are the DAB, DBC, DCA numbers? DAB 8, DBC 7, DCA 15 in meters. How much is that? 9.435 meters. 9.435 meters. Sir, if radius is not given, then we need not consider that radius. Sachin, that depends upon his requirement. No, if he's asking GMR value, definitely he will give radius. If we don't want GMR, they may not give the radius of conductors also. If their concentration is only to calculate the GMD. Okay? Yeah. Next. What about GMRs? All the three will be equal to the same value what we have done earlier. Okay, let me write quickly. GMR of phase A, phase B, and then phase C, all the three will be equal to 0.7788 into radius, that is 2 centimeters. So it will come to be 1.556 centimeters. 1.556 centimeters. Clear? So if R is different for all the three conductors, then the GMR will be average. You have to take geometric mean of these three. If the GMR of phase A, phase B, phase C are unequal, we should go for the geometric mean of these three as a GMR of each and every phase after doing transposition. After doing transposition, because you are taking average of the three inductances, right? Average of the three inductances. Okay, that depends upon. See, Sachin, if they have not given radius, I might be asking only for GMD. That's it. I might be asking only for GMD in that question without GMR. But here I am asking you both GMD and GMR by giving radius of conductors. Say GMR to be specified in any units, either it is in centimeters or meters, that according to our substitution. Okay. So let's continue. One more thing I will take. Very simple question. One more question. Just go through it now. Consider the following untransposed system carrying balanced currents. Balanced three-phase currents. Okay, consider the following untransposed system carrying balanced three-phase currents. Okay, the inductances of phase conductors are LA, LB, LC. LA, LB, LC are the inductances of the phase conductors. Okay, so I'll show you the three conductors here. Conductor A, conductor B, conductor C. A to B distance is 8 meters. B to C distance 8 meters. C to B distance 10 meters. Okay. So which of the following statement is correct? Which of the following? It's a MSQ question. Multiple select question. MSQ. Which of the following statement or statements is or correct. You please complete this one. I will move to next slide to write the options. And write the options. Nicola, I will show that in bundle conductors. Nicola, I will satisfy you in the bundle conductors, your doubt. Okay. So I am giving options now. Option A. LA, LB, LC. All three are complex. Three are complex. Option B. LA and LC are real. LA and LC are real. Okay, so these are the three conductors. I am saying LA, LB, LC are the inductances. Yeah, next. LA is only real number. Option D. LB and LC are complex numbers. Okay. Please check the options. Which options are correct? Which options are correct in this? Make it quick, please. It's an untransposed system. I have mentioned already. It's an untransposed system. Which option is correct or which options are correct? Anyway. See, according to this question, his interest is to know whether the inductance of conductor, phase conductor, is a real number or a complex number. That's it. Whether the inductance of the conductor is a real number or complex number, that's a question. See, just observe here, Babs. You see this system. See, when we can say the inductance is a complex number or real number means, just if you check the equations quickly, just listen, stop answering. Just look at the inductances we have derived. LA, it's having some real part and some imaginary part. In this imaginary part, what you are having here? Ratio between distances. Look my words, please. Ratio between distances. Between what? As we are staying at conductor A, I have to take the ratio between the phase A conductor to phase B and phase A conductor to phase C. A to B distance by A to C distance. That ratio I should take. If the ratio is 1, for example, if the B and C conductors are at equal distances from A, B and C conductors are at equal distances from A, then obviously those two distances are equal means ratio is 1. Ratio is 1 means natural logarithm of 1 is 0 and you don't get any imaginary part. See, if the distances are unequal from one phase conductor to the remaining two phase conductors, then only that imaginary term may come if it's an untransposed system. I think all of you getting my words. Okay, just if you look at this three-phase system, for example, if you are staying at A to B, A to C, both are equal. A to B, A to C, both are equal. So LA will be definitely a real number. Next, you stay at B. B to A, B to C. These two are unequal. As these two are unequal, B will be definitely complex number inductance. And what about C? C to A, C to B. These two also unequal. Then C also definitely complex. Okay, all of you getting this? Is this clear? I'm saying very simple, Rashmi. Just listen. Very simple. If you are staying at one conductor, check the distance from that conductor to remaining two conductors available. If the two distances are equal, no imaginary part. If the two distances are unequal, then the imaginary part will come. Okay, so I can say LA, the real number, since DAB and the DAC distance are equal. Okay, so LB, it's a complex number. What's the reason for this? DBC distance is not equals to DAB distance. Okay, so LC, it's also a complex number. What's the reason? DCA not equals to DBC. So from this, I can say C and D are correct answers. Okay. C and D are correct answers. Both are correct. C and D both are correct. Yeah, done. So this is a little about the inductance calculation. I'll show one simple problem to you. One simple problem. Just move ahead. I read it or not. All of you having this file? Oh, sorry. Somebody is complaining that it was not uploaded properly. I'm really sorry. I will do it definitely today. So you go through this question once. Explain you about it. So this inductance calculation is very, very important one. Particularly that complex number inductance is one of the untapped area in the GATE exam. In the IES prelims examination, they have asked 1 to 2 times that objective question. Objective question they have asked in the IES prelims, but in GATE examination, till now we didn't get any question with respect to complex number inductance. So be careful about it. Be careful about that inductance. At least you try to remember at least phase A inductance formula. Okay? Yeah. Go through this question. Is three-phase horizontal spacing transposed single conductor system has each conductor inductance as 1.2 millihenry by kilometer when it is carrying balanced currents. The diameter of each conductor is 2 centimeters. Assume that the middle conductor, 1, 2, 3, middle conductor is saying is at equal distances from the outer conductors. Means middle conductor to first outer conductor, middle conductor to second outer conductor. These two distances are equal. Okay. The distance between any one outer conductor to middle conductor in meters is. Okay. Yeah. Just look at this solution. What I am going to tell you. Simple, very simple question only. First of all, we have a horizontal spacing system, something like this. See, he has given all the conditions. He has given all the conditions in the problem. First one, he said horizontal transpose system. It's a transposer system carrying balanced currents. Carrying balanced currents. That also he said. And LA, LB, LC, all the three will be equal in this case. That is equals to 1.2 millihenry by kilometer. If you are confusing, you call it is simply L per phase also. L per phase 1.2 millihenry by kilometer. Yeah. Next, diameter of each conductor is 2 centimeters. Means what the radius of each wire? Radius of each wire will be 1 centimeter. And you see, this is a middle conductor. From this middle conductor to outer conductor 1 means A. To assume this distance is capital D. Similarly, from this middle conductor to outer conductor, second outer conductor C, this distance also equals to capital D. What is saying? That distance also equals to capital D. Okay, next. Examples. He is asking us to find the distance between any one outer conductor to middle. One outer conductor to middle means what is asking now? He is asking to calculate the value of capital D. That's it. Asking us to calculate. Yeah, please kindly send me the request now, Milan Kumar, please kindly. So I might be, so your message might be flown in some other, okay. Yeah, I will upload it, Samriti, Jayalakshmi, I will upload it, please kindly. Yeah, Listen. Now, L per phase already given. You know formula, right? What is the formula for L per phase? Point to ln of GMD by GMR. That we have to take. Okay. What is GMR? R dash 0.77 into 88 multiplied with radius. Okay. What is GMD? It's already transposed, said. So it is cube root of D into 2D. That we will dump and we'll calculate the value of capital D. That's it. Very simple question. Very simple. Just observe. So as L per phase formula, we know it is 0.2 natural logarithm GMD by GMR in terms of millihenry by kilometers. Okay. Whereas GMD value is cube root of DAB, DBC, ECA. We have D cube under cube root means D will come out and we will have cube root of D will come out and we will have cube root of. Anybody tell me please what is cube root of 2? What is cube root of 2? 1.25. 1.26. Okay. Times of capital D. Whereas GMR is 0.7788 multiplied with the radius of any one conductor 1 centimeter. I'll keep in meters. I'll keep that in meters. Okay. Now, therefore, L per phase number 1.2 equal to 0.2 natural logarithm 1.26 times capital D by 0.7788 into 10 power minus 2. Both I kept in meters. See, as if the denominator is in meter, obviously numerator also will be in meters. So D value we are going to get directly in terms of meters here. Meters. Okay, you try to solve this. You will be having 1.2 by 0.2 equals to natural logarithm of this number 1.26 D by 0.7788 10 power minus 2. Okay, and it may be 6, 6 and e power 6 you get, and D will come something like this e power 6 into 0.7788 into 10 power minus 2 by 1.26. This is the value of capital D. Anybody tell me please, how much is the value of capital D you are getting? 2.4935 meters. 2.4935 meters. Approximately 2.5 meters. 2.5 meters. Yes, Vishnu. Yes, Vishnu. As an approximation, you can take like that, Vishnu. As an approximation. 2.4935 meters. Yeah. One thing, listen. I want to tell a small conclusion for you. Just listen to me. I want to tell one small conclusion. In the examination, just look to the question what I am saying. You copy the same. I will make a modification in this and tell me. Three-phase horizontal spacing. Single conductor system has each conductor having an inductance of like this. They have given the question. Just observe this. Three-phase horizontal spacing single conductor system has each conductor inductance as 1.2 millihenry by kilometer. The diameter of each conductor is 2 centimeters. Assume that milliconductor, same thing. How to calculate this capital D value in this problem? How to calculate the value of capital D in this problem? Yeah, tell me please. How to calculate capital D value in this problem? See, actually, that formula for L per phase 0.2 ln of GMD by GMR. 0.2 ln of GMD by GMR, where GMD is cube root of DAB, DCA. I can use only for transposed system carrying balanced currents. Transposed system carrying balanced currents, but he didn't give it. Kindly listen. Don't guess. Just listen to me. Don't answer. Just listen to me. See, in this problem, he didn't mention about transposition as well as a balanced currents. Even though he didn't mention it, we have to assume it and we have to proceed with the same calculations. We have to assume that it is transposed and we have to assume that they are carrying balanced currents and we have to proceed with the same calculations as it is we have done in the previous problem. Revant Kumar. Revant Kumar. If listen, if his interest is to ask about untransposed system, they will mention it in the problem. If he didn't mention whether the system is transposed or untransposed, we have to assume it as transposed only all the time in the calculations. All of you getting this mark? What I am saying you? I need your response, please. Assumptions. Transposed. Carrying balanced currents. By making those assumptions, you should proceed with the. No. You should not assume it as symmetrical because distance are unequal, right? Distance are unequal, so you should not assume it as symmetrical. So your answer will be remain same at 2.49 meters. Same value you are going to get. If the question is asked on the untransposed system, he will mention it in the problem. If he didn't mention, we have to assume it as transposed. Yeah. Right. Next, let's continue. Let's continue with the next slide. Whereas here we can find D by inductance, B formula also. Need to think it is a transposed to solve. Okay, Prasad, after doing transposition, GMD of phase A, phase B, phase C are equal, right? Yeah, let's continue. Listen here. Listen this extension what I'm making. Actually, in the previous classes, maybe in the basic concepts of power transmission, we discussed about different voltage levels, like 132 kV, 220 kV, 400 kV we have taken, and then 765 kV. Like this, we have taken various voltage levels, right? Various voltage levels we have taken. Yeah. So I'm showing 52. If somebody is writing, please complete it quickly. I will wait for 10 seconds. Please complete it quickly. 52. Okay. Yeah. See this. See, these are the voltage levels which we have studied, and why we are going for higher and higher voltage levels like 400 kV and 75 kV. That's the question. Why we are moving to higher and higher voltage levels? See, Dinesh, Ramku, and all of you, for all the people I am saying you, one simple suggestion: do your calculations only in meters. Substitute the radius and distance between the conductors only in meters. Forget about centimeters. Even though they have given centimeter, convert that into meters. See, if you are taking natural logarithm of GMD by GMR, both GMD and GMR must be in the same units. Either we have to keep both in meters or we have to keep both in centimeters. Keep it in meters. That's same. Always. Yeah. Now, why we are going for higher and higher operating voltages here? To transfer a bulk amount of power at a good stability. Pmax value is going to be increased, we suggested. Not only that, cost of the system is going to be a bit less. Okay, power losses in the system also less. But you see, I said one disadvantage also there. While we are going for higher and higher operating voltages, we are getting some advantages. Okay, but we are having a disadvantage of corona. That's the issue what we are going to think now. According to the practical observation as well as the theoretical studies, the people are saying that about 220 kV levels, and of course 220 kV also, Corona may not be visible or corona may not be observable appreciably. Corona is not at all or not at a considerable level, not at a considerable level for a voltage levels 220 kV and below that. Whereas if you go for 400 kV and 75 kV level, corona is a considerable thing in our analysis. Okay, so I can say first statement for voltage levels less than or equals to 220 kV, corona can be neglected. Can be neglected because it is negligibly small, you can say, so that we can neglect the corona for the voltage level less than or equals to 220 kV. Whereas for voltage levels greater than 220 kV, such as 400 kV and 75 kV, corona is appreciably high. Appreciably high. It can't be neglected. That's the meaning. It can't be neglected. That's the meaning. Okay. Then what is this corona and all? What is this corona? Just have a look here. Corona. Already we have defined it, right? Corona. So if the electric field intensity on the surface of the conductor higher than the dielectric strength of medium, I'm not repeating the definition. I'm not repeating the definition, right? So then we will get some sort of ionization on the conductor surface that we are calling as corona. Because of high electric field intensity on the conductor surface, it will happen. That is one thing what you have to be clear, right? So occurs due to high electric field intensity on conductor surface. On the conductor surface. Conductor surface. Okay. Occurs due to high electric field intensity on the conductor surface. Next term. How this corona is physically happening? What is the physical significance of corona? How we can observe corona in the practical transmission lines? Okay, tell me please, how this corona will be practically visible, practically or physically? Physically, how we can say this corona is happening? One thing, we can get some sort of hissing sound from the conductor. We can get some sort of hissing sound from the conductor. Particularly, if you walk along a 765 kV line or 400 kV line, you used to get some sound from the conductor. Okay, so I can say hissing sound. Hissing sound from conductor. Hissing sound from the conductor. This is one way of observing the corona. Next one is glow. Glow on the surface of conductor. That's moreover light bluish glow. Light bluish glow on the surface of the conductor, or you can say violet glow on the surface of the conductor. Okay. Light bluish glow on conductor surface. On the conductor surface. As well as we'll get some sort of ozone gas released from the conductor. Ozone gas released from the conductor. Ozone gas release from the conductor. So these are the three physical observations of corona: hissing sound, light bluish glow, and then we have some ozone gas released from the conductor. Okay. See, actually, this sound and light, sound and light, simply I can say these are forms of energy. Sound is a form of energy. Light is also a form of energy. Listen. These energies in the transmission line are created due to corona, but we are not using it for any purpose. We are not using that light for any purpose, and we are not using that sound for any purpose. So these two are considered to be losses. So corona is basically an energy loss. Corona is basically an energy loss. Else, you can say it as power loss also. There is no mistake in it. So I can say corona is an energy loss. Energy loss, or you can say simply power loss. Corona is an energy loss, or you can say it's a power loss. Is it sound due to ionization? No. Gomadh Shankar, just all of you listen. If the electric field intensities continue to increase, first we will listen sound from the conductor. After that, if the electric field intensity exceeds a certain level, then you can observe the light. Following all of you, first sound will come, then we will get the light from the conductor. If the electric field intensity exceeds a certain number. Yeah, next. See, corona is a energy loss, or you are saying it's a power loss. So I can say for voltage more than 220 kV, I have two types of power loss in the system. One is a heating loss, so-called I square R loss in the conductor, and second one we can say corona loss in the conductor. But whereas for voltage less than or equals to 220 kV, we'll get only one power loss, that is I square R loss. Corona loss will be neglected. So I'll write here in the first step. Power loss here you get only I square R. And here the power loss means you get here I square R. Along with that, you can get the corona loss. Yes, Vikrant. Yes. During rainy season, dielectric strength of air will decrease. During rainy season. At that time, we can say corona will be more. Corona will be more in the rainy seasons and the winter seasons compared to summer. Okay, let's continue. So one disadvantage of corona, what you are saying, it is a energy loss, or you can say power loss. So I'll say, and one more thing, this corona is going to create a sort of radio interference. It's going to create a sort of radio interference on the communication systems, particularly wireless communication system, what we are going to talk here. Because of this discharge, corona discharge of high frequency discharge, this high frequency discharge may distort the wireless communication signals, and that is causing for some sort of disturbance in the communication signal, which we'll say as the radio interference, right? So I'll write here corona causes for radio interference. In wireless communication system. This is one of the major disadvantage of the corona communication system. Increasing power loss is okay, it may not be too high. Increasing power loss is okay, it may not be very, very high, but it is disturbing the other system. This is a main disadvantage of the corona, what we are going to say. And one more disadvantage is also there because of corona. One more disadvantage I'll show in the next slide. For example, we have two conductors, one beside the other, something like this. These are two conductors I'm showing, one beside the other. Conductor A, conductor B. Conductors A and B. Just listen to me. Very simple. Definitely, temperature, pressure will be affecting corona. Distribution lines, you don't see corona. Distribution lines. Yeah, listen. See, actually, corona itself a light bluish glow on the surface of conductor. Let me assume in this situation. For time being, on the surface of this conductor A, we have some light bluish glow formed due to corona. And on the surface of conductor B also, we have a light bluish glow on the surface of conductor like this. See, this corona is extending further and further because of increment in the electric field intensity further. Because of rise in the field intensity further and further, this corona may extend. Because of this extension, at some point of time, we can experience some sort of breakdown between the two conductors, something like this. We can experience some sort of breakdown between the two conductors, which we can say as electron avalanche breakdown happening due to severe corona, and it is causing for a short circuit fault in the system, causing for a short circuit fault in the system. This is one of the another disadvantage of the corona. Okay, so I can say electron avalanche breakdown, avalanche breakdown occurs due to severe corona, and it leads to short circuit fault, leads to short circuit, leads to short circuit fault. Okay, so I think all of you getting this. So three disadvantages I said. One is energy loss extra it is creating. Next disadvantage is the radio interference on communication system. Next disadvantage is the electron avalanche breakdown because of the corona. Okay. Particularly to overcome that communication interference, we should select the conductor. Particularly for the voltage levels more than 220 kV on the basis of electric field intensity concept. Or you can say on the concept of corona. We are going to discuss we are going to design the conductor, we are going to select the conductor for voltage levels more than 220 kV. Okay, so I'll write it anyhow. So I'll say here, avalanche breakdown is a breakdown which happens generally in a normal diode because of high electric field intensity. We use to get that type of breakdown. Yeah, kindly listen. So for voltage levels more than 220 kV, conductor selection done on the basis of corona. Conductor selection done on the basis of corona. Or you can say electric field intensity. Okay, whereas for voltage levels less than or equals to 220 kV, is it required to consider corona? No, we no need to consider corona. If we no need to consider corona, on what basis we will be selecting the conductor size? Anybody? In the previous class also we have discussed. 220 kV line means it is a feeder, right? Transmission line we are talking, that's a feeder. So it will be selected on the basis of simply current rating, or you can say current density. Okay, for this level, conductor selection done based on current rating, or you can say current density. Current rating, or you can say current density. Thermal stability also you can say. Thermal limit of the conductor. That does not mean that we are neglecting the current rating in second case. Means for voltages above 220 kV, we have to consider the current rating also. There is no doubt about it. But primary criteria is a corona. Okay, first we should select the type of conductor based on corona. Then we should think about the areas of these conductors with respect to the current rating also. Okay, yeah. Now, as a conclusion, what I want to tell here is, from this point onwards, our aim is to reduce corona in the power transmission lines. Right? So to reduce corona, only one option here, we have to reduce the electric field intensity. Now, electric field intensity depends upon what factors. That we'll discuss first. Thereafter, we'll think about reduction of corona. Okay. So for that purpose, I'm taking one single phase 2-wire system electric field intensity formula. Single phase 2-wire system electric field intensity. Okay. Single phase two wire system. Electric field. Yeah. Practically, that glow will be visible. Glow will be visible practically. Okay, I will show you after some time. Pause. See this single phase two wire system. I'm showing only two conductors here. It's forward conductor A, and you have this as a return conductor B. Something like this. Forward and return conductors will show like this. This is A, you can call, and this is B. And distance between these two conductors I am showing as a capital D, and radius of each wire is smaller. Radius of each wire is small or near. Okay, next. Look here. I am applying some voltage to this conductor A. I am applying some voltage to this conductor A. So I am showing it V. This is the applied voltage to conductor A. That's it. Conductor A. Applied voltage to conductor A. Only to the conductor A. Not between A and B. Not between A and B. It's only to conductor A. We are applying a voltage of V. Okay, next thing. Listen, please. See, particularly if you talk about only conductor A, where the electric field intensity is very high. Where the electric field intensity is very high. Generally, the people use it to say on the surface of conductor, the field intensity is very high. That's okay. How is the field intensity inside the conductor? How is the field intensity inside the conductor? Anybody please tell me? Nobody is answering. What is the field intensity inside the conductor and what is the field intensity on the surface of conductor? Inside it is zero. Inside it is zero, on the surface it is maximum. This is the general scenario. I'll tell you why it is happening and all. So electric field intensity equals to zero inside the conductor. Inside the conductor. And that electric field intensity is a maximum value on the surface of conductor. On the surface of conductor, that field intensity is a maximum value. Done. Next. Listen. Why it is happening? Why it is zero inside? Why it is maximum on the surface? Okay. Any other name you say for field intensity? Any other name? Any other name you can say for field intensity? Sometimes you can call it as stress, electrostatic stress. You can call this as electrostatic stress. Well, sometimes you can call it as field gradient, or you can say voltage gradient. Any term. Voltage gradient, field gradient, electrostatic stress, all these terms will be same. Okay. What do you mean by gradient of voltage in mathematical term? Gradient of voltage in mathematical term is del V. Del V. Gradient of voltage is del V. So you know, you might have seen this formula like E bar equals to minus del V. You might have seen a formula like E bar equals to minus del V. E bar equals to minus del V. What is the del V? Del V means it is dou V by dou X AX bar plus dou V by dou Y AY bar plus dou V by dou Z AZ bar. Like that. Okay, del V in the sense dou V by dou X AX bar plus dou V by dou Y AY bar plus dou V by dou Z AZ bar. Okay, next thing. Listen please. Next thing. Listen. See, I'll write simply Ex is equals to magnitude. Magnitude of Ex equals to rate of change in the voltage with respect to X. Rate of change in the voltage with respect to X. That you can see. Okay, one simple question I am asking you. One simple question. What is the voltage on the surface of conductor? Voltage. What is the voltage on the surface of conductor? Anybody please tell me? V. Voltage on the surface of conductor will be V only. What is voltage inside the conductor? What is voltage inside the conductor? Anybody? What is voltage inside the conductor? V only. Why it is zero? Why it is less than V? It will be V, right? You are applying a voltage of V to the conductor, right? Listen to me, please. As you are applying a voltage V to the conductor, obviously inside the conductor also you have a voltage of V only. There is no change in the voltage, provided that the conductor is an ideal conductor. All of you listening to this? All of you listening to this or not? I need your response, please. Nobody is responding. Yeah. As you are applying a voltage V to the conductor, inside the conductor voltage will be V, as well as on the surface of conductor also voltage will be V only. Now the question is, this is point number one I am considering inside the conductor. Point number one I am considering inside the conductor. I am moving from this point 1 to point 2 inside the conductor only. I am moving from one point to other point. What is the change in the voltage? What is the change in the voltage you get? What's the change in the voltage? Zero. That's what the field intensity, right? Field intensity is nothing but change in the voltage with respect to distance. Change in the voltage with respect to movement. So inside the conductor, even though you are moving from one place to other place, you are not experiencing any potential change. As you are not experiencing any potential change, field intensity inside the conductor will be zero. Gradient is zero inside the conductor. Indication is that we don't have any change in the voltage inside the conductor. That's a simple term. So I think all of you getting this. Is it okay? It is one of the easiest way of understanding. One of the easiest way of understanding. Next, on the surface of conductor, we have a voltage V. On the surface of conductor, we have a voltage of V. And if you are moving from surface to out, then outside we don't have any excitation. Definitely there is a change in the voltage. If you are moving from surface of the conductor to out, definitely there is a change in the voltage. So we have the field intensity on the surface of the conductor. On the surface of the conductor. So we used to have highest field intensity on the surface of conductor, zero field intensity inside the conductor. Okay, right. So next I will write the formula for the E maximum. I will come back within 1 minute. Please. So I have resumed audio video on screen. Kindly follow it. So I will be giving the expression for this maximum field intensity, what you are getting on the surface of the conductor, this one. So this is the maximum field intensity, what you are going to experience. The field intensity formula I am giving. So I'm not going with any derivation. I'm not going with any derivation. So on the surface of conductor, on the surface of conductor, electric field intensity is formula I'm saying. Applied voltage is what? V. Applied voltage is V. So I'll take applied voltage to the conductor V in the numerator by small r into ln of d by r. Small r into ln of d by r. And this will be in the units of kilovolts per centimeter or volts per meter according to the substitution. So V by small r into ln of d by r. D by r. So that is a field intensity on the surface of the conductor. Okay. Yeah, difference between gradient and electrical intensity both will be same. Gradient and voltage, sorry, electrical intensity both are same. Yeah, listen please. Now our aim is to reduce the field intensity with what we have started now. So I'll say to reduce field intensity or to reduce corona, whatever it is. To reduce corona, or you can say to reduce the electric field intensity. Electric field intensity. What are the various steps we have to take? What are the various modifications we have to take in this equation? That you have to kindly observe. Okay. One, to reduce the electric field intensity, one option is reduce the operating voltage. Reduce the operating voltage. D is the distance between conductors. I am sorry, I have shown small d there. I have shown capital D in the diagram. Capital D, distance between the conductors. Yeah, listen please. Reduce the operating voltage is one option. Reduce operating voltage of the system is one option. Next option. Increase the radius of the conductors. Increasing radius of conductors means overall denominator value will go high. So field intensity will be definitely reduced. So increase the radius of the conductors. Increase radius of conductors. Okay, next. Third one. See, I will be increasing distance between the conductors. By that way, denominator value will go high and electric field intensity will decrease. So increase the distance between the conductors. Increase the distance between conductors. These are the options we have. See one thing, first one. Reducing operating voltage is not suggestible. Why? Why in the sense? See, we are going for higher and higher operating voltage levels in order to have good maximum power transfer capability as well as good stability. But on the way of that, we are getting an undesirable phenomena so-called corona. So to reduce that corona, again reducing operating voltage is not suggestible. To reduce corona, reducing operating voltage is not suggestible. So this is not suggestible in the view of maximum power transfer capacity. Okay, next thing. Two options you have for that. One, increase the radius of conductor, one option. Next one is the increasing distance between the conductors. Which one you choose among these two? Increasing radius or increasing distance between conductors? Anybody tell me please? Increasing radius of conductors means, listen. Increasing radius of conductors means definitely volume of the conductor material required may be more. Obviously, cost of system is going to be increased. So I can say volume of conductor material required is more. Volume of the conductor material required is more. That's a disadvantage. So obviously cost of system is going to be increased. What will happen if you want to increase the distance between conductors? Tell me please. What will happen to increase the distance between the conductors? See, we have to increase the cross arm length. Cross arm length has to be increased here. Cross arm length has to be increased. Right? Increasing the distance between the conductors means we have to increase the cross arm length of the tower. So obviously size and cost of tower definitely increases. Cost of the tower is going to be increased. Size of the tower also going to be increased. Not only that, because of increment in the distance between the conductors, what will happen to inductance value? Inductance per phase definitely increases, because you know that the inductance formula already we have written. Point to ln of GMD by GMR. Else we say D by R dash. Point to ln of D by R dash. If distance between conductors was increased, inductance value is going to be increased. Because of that increment in the inductance value, reactance value increases. Reactance value increases. Okay, reactance value was increasing means obviously maximum power transfer capacity decreases now. Maximum power transfer capacity is going to be reduced, because you know formula for P maximum, Vs into Vr by X. Vs into Vr by X. If X value was increasing, definitely maximum power transfer capacity is going to be reduced. So these are various disadvantages we are getting of increasing the distance between the conductors. Is it suggestible now? Is it suggestible? No, it is also not suggestible. All of you getting my words? See, actually, three options I said now. First option, reducing operating voltage, not suggested. Second option, increasing the radius of the conductor. Volume of material required is more. Then also it is not suggestible. Next one is increasing distance between the conductors. Because of that, cross arm length required is more. Inductance value increases. Reactance value increases. Maximum power transfer capacity is decreasing. So these three options are not at all suggested. Then how to reduce the field intensity or corona, right? Already we suggested some conductors to reduce corona. One is expanded ACSR. I think all of you remembered it. Expanded ACSR conductor is one option we said. Yes or no? Expanded ACSR is one thing, and other one is a hollow conductor. Other one is a hollow conductor. But those two will limit that corona only up to certain extent. Those two conductors will limit the corona up to certain extent only. Beyond that extent, if you want to reduce corona, we have to move to bundle conductor system. Bundle conductor system has to be used in order to reduce the corona. Okay, so I can say the next heading here, bundle conductors. Bundle conductors. Since the main aim of these bundle conductors will be to reduce corona or to reduce electric field intensity or to reduce the radio interference on communication systems. Radio interference on communication systems. Okay, yeah, simple, very simple. Just listen to my words, what I'm saying. Listen to my words. In the bundle conductor system, we used to keep two or more conductors in each phase. For example, phase A, I'll keep three conductors. A1, A2, A3, phase A. Phase B, three conductors, B1, B2, B3. Phase C, three conductors, C1, C2, C3. Okay, number of conductors we are going to keep in each and every phase. These are going to be called generally subconductors. These are going to be called as subconductors. Okay, yeah. Not only that. I'll show you first. I'll show you the diagram, then I will go for the definition. So Actually, this is a single conductor system or single conductor. You can say a single conductor. This is a radius of this wire is smaller. Okay. This we are going to replace. This we are going to replace with the number of conductors in the phase A. Number of conductors in the phase A. Let's say three. Let's say three conductors in the phase A. So it is A1, I'll say, and similarly A2 and A3. A1, A2, and I'm showing A3 here, something like this. A1, A2, A3. Okay, and this whole we are going to call as phase A. Phase A bundle conductor. Phase A bundle conductor. And A1, A2, A3. These three are going to be known as subconductors. 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 Next thing. Listen, please. Listen, all of you. If the single conductor is operating at a voltage V, single conductor is operating at a voltage V, then what will be the voltage of A1, A2, A3? Anybody please tell me? What will be the voltage of A1, A2, A3? Will be remain same. V only. Because simply one conductor we are dividing into three. One conductor we are dividing into three. So obviously A1, A2, A3 conductors will be operating at the same voltage of V here. Same voltage of V. Next. Currents you observe. Conductor A is carrying a current of I at an angle 0 degree. A1, I1 at an angle 0. A2, I2 at an angle 0. A3, I3 at an angle 0. Like this we have currents. See, all the three currents are in phase currents. That's the meaning. All the three currents are in phase currents. In phase currents. Next thing. Conductor A1 radius. I'll say R1 for time being. A2, R2, A3 is something like R3. All the three might be equal most of the times. All the three might be equal most of the times. Next thing. Listen, please. Listen. See. You talk in the way of electromagnetic theory. I have a charge Q. I have a big charge Q. That I'm cutting into three parts. A charge Q we are cutting into three parts, coming like Q by 3, Q by 3, Q by 3. Okay, so this is a charge Q. It was cut into three parts. Q by 3, Q by 3, Q by 3, Q by 3, Q by 3. Okay, now I will define the bundle conductor system. Just follow the words, what I am saying, I will write it. In bundle conductor system, each phase consisting two or more number of subconductors, running in parallel, definitely running in parallel, operating at same voltage, carrying same phase current, and charge will be equally distributed. Among the subconductors. Following all of you. Okay, so I'll say in the next slide. Just look here. In bundle conductor system, is each phase consists two or more number of subconductors, running in parallel, operating at same voltage, carrying in phase currents. Carrying in phase currents. Operating at same voltage, comma, carrying in phase currents, and charge will be equally distributed. Will be equally distributed among the subconductors. Subconductors. Okay, so I will be implementing each and every statement in a sequence. Charge is depending on its size generally. Charge depends upon its size. So this is a way how you have to understand. Strictly speaking, this is a conductor A earlier. Now I am dividing that into three: A1, A2, A3. A1, A2, A3, like this. It's a bundle, and above one is a single conductor. Above one is a single conductor. This is a way of division. That's the way of the division. Okay? Yeah. Next. I'll tell you what is the reason of bundle conductor. I said already the aim to reduce corona, and I will show you how that field intensity or corona is going to be reduced after a little time. Next. See, both systems should have same power rating. Both systems should have same power rating. Same power rating. In the sense here, V into I must be equals to sum of these three powers. V into I1 plus V into I2 plus V into I3. Okay. So I'll say here, same power rating is one of the conditions we have to maintain, definitely. Same power rating is one of the conditions we have to maintain. V into I, it's a phase power, equals to V into I1, V into I2 plus V into I3. V into I1 plus V into I2 plus V into I3 we can see. Okay, next. Next. Let's continue. I'll tell you what that equal distribution, unequal distribution kindly is. Next one. See, earlier I said that if you are increasing radius of conductors, definitely corona will be decreasing, but volume of conductor material required is more. Volume of material required is more. So we should keep our volume as it is. We should keep the volume of the material required as it is. In the sense, I'll tell you, volume of this phase A conductor in the single conductor system, volume of this bundle conductor phase A must be equal. These two volumes must be equal. What's the volume of phase A here? What's the volume of phase A? Pi r square is the area of cross section multiplied with length. Pi r square multiplied with length is the area here. What's the area A1? Pi r1 square L. Area A2, pi r2 square L. Area of A3, pi r3 square L. Sum of these three volumes must be equal to volume of conductor A. Okay, so I can say here, same volume of material shall be used. Means single conductor pi r square L, here pi r1 square L, pi r2 square L, pi r3 square L. Like this we can say, L will be cancelled out, pi also cancelled out, and radius square of single conductor equals to sum of the radii squares of the subconductors. Clear? I'll come to your doubt. Please kindly listen sometime, Milan Kumar. It's not stranded. Okay, next thing. See, rather than three, if you have n subconductors, it will come to be R1 square plus R2 square plus R3 square and so on up to Rn square. For n subconductors, subconductors. R square equals to R1 square plus R2 square plus and so on up to Rn square. Okay, now if you assume that all the subconductors are having of equal radius, right? Each and every subconductor is having same radius. Then, therefore, R square equals to N into R1 square, you can write. R square will be equals to N into R1 square. N into R1 square. Okay, then what is the value of R1 now? R1 will be coming like R by root N. R1 is equals to R by root N. This R1 is a radius of each subconductor. Radius of each subconductor. So radius of each subconductor equals to R by root N, where N will be the number of subconductors what we are going to keep in each phase. N will be the number of subconductors in each phase. Number of subconductors in each phase. Okay, so for example, if you have three subconductors like this, and all the three are having equal size, what will be that value? That will be R by root 3, right? If R1 equals to R2 equals to R3, then this R1 value will come to be R by root 3. R1 value will come to be R by root 3. So I think all of you getting this? I think you are clear about this one. Yeah. So I will be extending this after having a little break of 10 minutes. After 10 minutes break, I will be extending with this bundle conductors. Okay. 10 minutes break. I have resumed audio, video, and screen. Yeah. So next, so let's continue. See how that electric field intensity is getting reduced if you are converting one conductor into a number of conductors running in parallel. How that electric field intensity is going to be reduced. That's the point which we are going to discuss now. See, for example, I'll say we have one conductor, phase A conductor. You say something like this. It's a phase A conductor with some radius of smaller. Okay, so it's a single conductor, right? And this I am dividing into two subconductors, A1, A2. Two subconductors, A1 and A2. This is A1, and I'm showing just beside to this as A2. A1 and A2. We look here. A1, A2. Next thing. Radius is R1 here, and this radius is also R1. Same thing, same thing. What is that R1 value? What will be that R1 value here? R1 is nothing but the value R by root 2. Because of same volume we said, pi r square must be equals to pi r1 square plus pi r1 square. So R1 will come to be R by root 2. Okay, next thing. Charge on this conductor A is Q. What is the charge on A1 conductor? Q by 2. What is charge on A2 conductor? Also Q by 2. Q by 2, Q by 2. Charges on A1 and A2 conductors are equal. Next thing. Spacing between A1 and A2 is S. So this is a letter, S is a letter I am using to define spacing between subconductors. S is a spacing between subconductors. Look here, please. Look here. S is the spacing between subconductors. Next thing. Listen all of you. Very simple thing. See, what is this Q? Is it a line charge or point charge? Line. It's a transmission line conductor, right? Transmission line conductor, so it's a line charge Q. And Q by 2 also line charges. See, starting class, we have taken up some equation for electric field intensity. Starting class, we have taken up a expression for the electric field intensity, something like Q by 2 pi epsilon into X. Q by 2 pi epsilon into X at a distance of X from the line charge. All of you remembered this? All of you remembered this? Yes or no? Tell me, please. All of you remembered this equation. E is equals to Q by 2 pi epsilon X. Okay, now the thing is, what is the field intensity on this conductor surface? Means single conductor surface. What is the field intensity on the single conductor surface? I'll write here. On the single conductor surface, electric field intensity formula will come to be Q by 2 pi epsilon into radius. Q by 2 pi epsilon into radius. Okay, done. This is a bundle, right? This is a bundle. Tell me, please, on bundle conductor surface means where I have to find the field intensity. On the bundle conductor surface means where I have to find the field intensity. Is it on A1 or A2 or anyone? I need your response. On what subconductor we have to find the field intensity? Is it A1, A2 or anyone among these two? Anyone you can say, anyone, not some, anyone. Okay, listen please. See, I want to find the field intensity on this A1 conductor, something like this as EA1. So I'll write here on bundle conductor, on the bundle conductor, EA1. Very simple. See, listen, all of you, stop writing. Just listen. Here we have two conductors now. First, we should find it on A1. Then we should look the effect of A2 on A1 also. We should look the effect of A2 on A1. Okay. On the A1 itself, the field intensity will be Q by 2 pi epsilon R1 on the conductor A1, Q by 2, charge is Q by 2. Look here, Q by 2 by 2 pi epsilon into R1. Next thing, due to A2, what is the field intensity at this place? Due to A2, what is the field intensity at this place? It will be Q by 2 by 2 pi epsilon into spacing is S. Spacing is S. All of you understanding this? All of you understanding? Please tell me. In the previous case of single conductor, we have only one conductor, so we get only one number. But in the other case of bundle, I have two conductors. So if you want to find out field intensity at one place, any one place, I will have two numbers by superposition. Because of A1, some number you get. Because of A2, some number you get. The resultant is the field intensity at that location where you are staying. Okay, next thing. One minute, Jessica and Srinaya, just listen to me. Practically speaking, this S value is like 40 centimeters, 50 centimeters in that range. S value is like 40 centimeters or 50 centimeters. And this radius, small r1, it will be very low, like 2 or 3 centimeters. In that perspective, this radius R1 is very, very less compared to S value. Practically speaking, radius of subconductor is very, very low compared to spacing between the subconductors. In the tube, either it is S plus R1 or S minus R1, you will get S only. Following? Okay, I'll move to the next slide. EA1 I'm going to rewrite now. EA1, which is Q by 2 by epsilon into 1 by R1 plus 1 by S. 1 by R1 plus 1 by S. But you know R1 is very, very low compared to S. R1 is very, very low compared to S. Definitely 1 by R1 value will be very, very high compared to 1 by S. 1 by R1 is very, very high compared to 1 by S. Therefore, electric field intensity EA1 will come approximately Q by 2 by epsilon into 1 by R1. 1 by R1. What is that R1 you have? R by root 2. So it will come to be Q by 2 by 2 pi epsilon into 1 by R by root. 1 by R by root. And let me simplify this quickly. And we will get that comparison now. So electric field intensity on the bundle conductor surface will be equals to, you will get root 2 by 2 approximately. Root 2 by 2 into Q by 2 pi epsilon radius. Root 2 by 2 is the value 1 by root 2. And Q by 2 pi epsilon R is nothing but electric field intensity on the single conductor. Electric field intensity on the single conductor. Okay. For example, if you have 3 subconductors, what will happen? 3 subconductors, what will happen? Anybody please tell me. 3 subconductors means you will get Q by 3 by 2 pi epsilon R1. R1 value will be R by root 3. R by root 3. And remaining terms are neglected little bit. Then, as an extension, what you get here is obviously 1 by root 3 into EA for 3 subconductors. For 4 subconductors, 1 by root 4. For 5 subconductors, 1 by root 5. 6 subconductors, 1 by root 6. So for n subconductors in the bundle, so electric field intensity on the bundle conductor will be approximately equals to, approximately, not exact, approximately equals to 1 by root n times of electric field intensity on the single conductor system. Electric field intensity on the single conductor system. Okay. So from this point onwards, I think you are very clear that if you are replacing one conductor with a number of conductors with some spacing, means if we convert a single conductor system to bundle, single conductor system to bundle. Definitely, electric field intensity on the bundle conductor system will be less compared to the field intensity on the single conductor system. So I think all of you getting this point. Is it okay? Can you move ahead? So I'll say here, electric field intensity on the bundle conductor system was definitely less compared to electric field intensity on the single conductor system. This is a comparison. Comparison between bundle and single conductors. Next thing. Let's continue with one more point here in the bundle conductors only, in the bundle conductors. Next, for example, just look. This is a single conductor here to be converted into bundle with two subconductors. It's some spacing between them. Okay, next, look here. See, we will be looking in the manner of tower. We will be looking in the manner of tower. See, actually, one more thing I want to tell you. For example, if you have 4, let's say 4 rather than 2, I'll have 4. It's a single conductor, big one. Single conductor, big one. This we are converting into bundle. Bundle consisting 4 subconductors like this. Subconductors A1, A2, A3, A4 you take if you want. A1, A2, A3, A4. See, in order to maintain spacing between these subconductors as equal. Spacing between these subconductors as equal throughout the length of the transmission line wire. Throughout the length of the transmission line wire, if you want to keep the spacing as equal, we use it to keep some sort of spacer. We'll be keeping some sort of spacer between the subconductors. This is spacer. Spacer will keep between the subconductors to maintain the spacing between subconductors as constant throughout the length. Maintain spacing as constant. Spacing as constant throughout the length. Maybe successively at each and every 50 meters length. Sir, here we have taken only on one conductor is sufficient, Bhavana. Why you are bothering about summation again? Not total bundle. Only one subconductor you have to find. Because the field intensity at that place decides the corona. That's it, not the summation. Yeah, listen please. See, successively for each and every 50 meters length, we used to keep this spacer. So that the spacing is going to be maintained as constant throughout the length. With what material we have to take up this one? With what material we have to construct this? Tell me please. Yeah. What material? Metal or insulator? Metal. We'll be going with metal. It's a metallic spacer. Metallic spacer. Because all the 4 conductors belongs to the same phase, right? Even though you're using insulator or metal, it's not going to make any change. So we are going with a metallic spacer to have a good mechanical strength. Now, for example, you observe now, to run this single conductor on the tower, I might be having a cross arm, something like this, and it was an insulator kept in this manner. And whereas to run this bundle, is it one insulator sufficient for us? Only one insulator is sufficient, or we have to go with the number of insulators now? Let us say 2 insulators I am using. Just look my words, what I am saying. Look my words, please. So I am using 2 insulators. This is the first insulator, and this was second insulator. To hold the complete bundle, I am keeping 2 insulators. My question is, for example, if I am using 20 discs in the string, 20 discs in this particular string, how many discs I have to use in the string 1 and string 2 of bundle? The bundle conductor, what will be the number of insulator discs in each string? Will it be 20, 20 or 10, 10? 20, 20 we have to use, not 10, 10. Because each conductor is operating at the same voltage of single conductor, right? For example, if this conductor is operating at a voltage 400 kV by root 3, then definitely all these 4 conductors will be operating at same voltage of 400 kV by root 3. So obviously the insulation level required to be same as it is compared to single conductor system. Here the number of discs is 20, here also number 20. So in that way, number of string insulators required to run the bundle conductor system will be greater compared to single conductor system. So definitely cost of bundle conductor system will be more compared to single conductor system. But we are going to get many advantages even though we are spending extra cost. We are going to get many advantages of the bundle conductor system, which we'll be discussing further. So one thing is clear, that cost of bundle conductor system is more compared to single conductor system. Okay, done. So I'll show some images to you with respect to this bundle conductors. I'll show some images. Kindly go through it. Screen, is it okay? Audio, video on screen. Audio, video on screen. Is it okay? All of you there? Yeah, okay, done. So let me continue. With this. I'll show some images. Just go through it once. You see, this is a bundle conductor of 4 subconductors. This is a spacer, what I said just now. It's a spacer, and these are 4 conductors. Okay, I'll show some more images which I collected outside practically. Just have a look at this bundle conductor system. I think all of you looking at this, just observe this. See, I'll tell. This 1, 2, 3. It's one 3-phase circuit. This one 3-phase circuit, you can call it as A1, B1, C1. One 3-phase circuit. Okay. Next, on the other side, you observe. On the other side also, you can observe one more 3-phase circuit. If possible, just check. This is one circuit, one phase, and this is a second phase, and this is a third phase, something like this. Okay, so you call it is A2, B2, C2. It's a double circuit line, basically what I am saying you. It's a double circuit line, and each and every one is a bundle conductor, right? So it's a bundle, right? It's a bundle. You can observe group of conductors in that phase. That's a bundle. Okay, next thing, I'll tell you. Next, one more thing. You can observe one wire on the top of the tower. Are you looking at this one? Yeah, I need your response, please. Are you looking at this? On the top of the tower, there is one extra wire. Extra wire, yes or no? Yeah. So this wire is a ground wire, or you can say earth wire, lightning shield wire, lightning shield wire, lightning shield wire. Okay. See, one more thing. Let me tell you one more thing. Maybe at this place, that power conductor is taking some diversion. Power conductor is taking some diversion. That's why they have used these insulators in this fashion. These are strain insulators now. Strain type spring. This will be called as strain type spring. Strain type spring. Okay, I'll show in the next image. I'll show in the next image also. Just have a look. Yeah, we have jumpers here. We have jumpers here. I will show those jumpers also. Because to have a direct contact between these two conductors, we have to use some wire, something like this. This is called a jumper. I'll show in the next slide. Please note it. I'm showing slide possible. I'll show here only. Just check. Yeah, you see, for example, this you consider this one. Okay, so from this point to this point you want to connect. For example, if this connection is not there, you don't have any contact between this conductor to this conductor, right? You don't have a contact between this conductor to this conductor if you don't have this connection. Yes or no? To have that connection, we are using a bundle conductor connection, something like this. This is called a jumper. This is called as jumper. Okay, that's called a jumper. Next, how many strings we are using here? Anybody? Can you count? Can you count how many strings we have here? How many subconductors we have? Can you count? How many subconductors we have? How many strings we have? Count. Strings. Four strings. I'll show even an elaborate image if possible. Just observe here. Just observe in this one. Yeah. How many strings we have? It is looking to be 3, but it is 4 exactly. Looking to be 3, but exactly speaking, it is 4 strings here. 4 strings. How many subconductors? How many subconductors? 6 subconductors in each phase. 6 subconductors in each phase. Conductors in each phase. Okay, and these are 4 strings. 4 strings per phase. Per phase. 4 strings per phase. Yeah. Next. Okay. So I think all of you getting this. I'll show one more image to you. One more image. Just look. Yeah, you try to observe this outside. If there is an access for you to reach the tower location, if there is an access for you, just try to observe this type of color coding. That will tell you which phase is on top, which phase is on middle, which phase is at bottom. Following all of you. Starting from the generating station, you will have the color codings like RYB, red, yellow, blue, and how these phases are running on the tower. Which phase is on top, which phase is at middle, which phase is at bottom. Okay, to know that, this will be more helpful. So according to this, what I can say is a topmost phase is a blue color, B, and middle one is red, bottom one is yellow. Okay, just observe it. If there is a double circuit line, better you can observe in that. The jumpers are not meant for transmission. Jumpers are not meant for transposition. How many strings we have to use per phase means that depends upon the weight of the conductor. If the weight of the conductor is very high, it may be needed to go for 4 strings. If the weight of the conductor is less, it may be required to go for only 2 strings also. Not only the insulation level, weight of the conductor, how much that insulator has to hold will decide how many strings we have to use. Okay. How to decide BRY, why not RYB? See, they have given in this manner on the tower. On the tower, they have given as an indication like this. It's a blue color indication, blue. And this is a red color indication, R. And this is a what we call yellow indication. Yellow indication, it's a Y. Yeah, BRY. Next, let's continue. There is a rectangular box you are asking me. Color coding will help in the transposition. Color coding will help in the transposition. So can we say voltage level by seeing number? I will no, voltage level you can't say by looking at the number of lines. I'll tell you the method to tell the voltage level. 1 minute, please. 1 minute. I'll come back. Yeah. Continue. Okay. Somebody asked about this box, this rectangular box. It's not box actually. It's a ring. It's the ring, which we are going to name it as generally corona ring. This ring, we are going to call it as corona ring. Corona ring. Okay? Corona ring. Corona ring. Corona ring. So corona ring main aim is to reduce corona. Actually, at fine and sharp edges, we know that electric field intensity is high. At fine and sharp edges, we know that electric field intensity is high, and at that spot, we can experience more corona. Yes or no? So in order to reduce that corona, we will be connecting this ring. By that way, whatever the high electric field intensity we have at this spot, at this junction spot, it will be distributed on this. It will be distributed on this, so that net electric field intensity is going to be reduced. Following all of you? All of you understanding the meaning of why jumpers are used just for connection? Just for connection, they are using jumper. Without jumper, you don't have connection from one side of the tower to other side of tower, right? Yeah. Simple. All of you getting this one? What I am saying? At this point, field intensity is very, very high. To reduce that field intensity, we are connecting a ring of this type to this point so that the charge is getting distributed on the ring. Charge is getting distributed on the ring so that field intensity is going to be reduced. So corona ring is used to reduce electric field intensity at the junction points. It's not okay. Guard ring sometimes we can call it if you want. Let's discriminate here. It's 4. Kindly, there is a overlap. That's why I'm saying it. There is 4. One string you can't see in that picture. Let's move ahead. See, from this point onwards, our aim is to think about GMR, GMD calculations. GMR, GMD calculations for bundle conductors. Okay. Yeah. So next heading I am taking up GMR and GMD calculations. For bundle conductors. Three-phase bundle conductor system. Three-phase bundle conductor system. Okay. So let me show as a schematic. I am showing one tower here. That is structure, something like this. Tower. Okay. So I am showing the cross arms. Only one circuit. I am taking one circuit. is a cross arm corresponding to phase A, cross arm corresponding to phase B, and it's a cross arm corresponding to phase C. ABC phases, cross arms. Next, listen to me. So in each phase, I'm keeping two conductors. I'm keeping only two conductors in each phase. Phase A, A1, A2, B, B1, B2, C, C1, C2. Okay, so I'll show it. Two conductors in the phase A, like A1, A2. Two conductors in the phase B, like B1, B2. Two conductors in the phase C, like C1, C2. Right? A1, A2, B1, B2, C1, C2. Let's introduce a notation quickly. Let's introduce a notation R1, radius of each subconductor. Radius of each subconductor. Okay, next. Gap between A1 and A2 is S. Of course, between B1, B2 also S we have. C1, C2 also we have S. S is a spacing between subconductors. S is a spacing between subconductors. Spacing between subconductors. Okay, next. Between A and B, the distance I am saying as capital D. Between B and C also we have a distance of capital D here. Between C and A also we have a distance of capital. So capital D is a spacing between or distance between the phases. Capital D is the distance between phases. Distance between phases. Okay, done. Next. Next thing. See, from this practical observation of bundle, maybe this one. Practical observation of this bundle. How is the distance between the phases means capital D value? What we have shown. Distance between the phases compared to spacing between subconductors. How is the distance between the phase conductors compared to spacing S? Very, very high. Yeah, this you have to observe. Just listen to me. Yes or no? Capital D value was very, very high compared to the value of S for a practical system. Okay, so I'll write it. SC is very, very less compared to capital D. That's a statement. Already I said R1 is very, very less compared to S. Is it okay? Please kindly confirm audio video on screen. There was a power failure. Okay, fine. So R1 is very, very less compared to S. S is very, very low compared to D for a practical bundle conductor system. This is for practical bundle conductor system. Practical bundle conductor system. Okay, so let's continue. Let's continue with this. So now GMR we have to calculate. GMR we have to calculate. So how many phases we have now? 3 phases. Phase A, phase B, phase C. So I'll calculate GMR of the phase A, GMR of phase B, GMR of the phase C. After calculating these 3 GMRs, GMR of the system will be geometric mean of these 3. Approximately I'm saying it. Approximately we are saying it. Okay, first I'll take phase A, only phase A. So you have 2 conductors in the phase A. This is A1 and this is A2. Spacing between A1 and A2 is S we are showing. Radius is R1. Radius is R1. Very simple to write. Just observe. I'm not going with derivation to confuse you. I'm not going with derivation to confuse you. Just follow it, what I'm saying. So let's continue. Listen here. See, both are carrying same phase current. Both are carrying same phase current. Maybe this is carrying I1 at an angle 0 degree. This is also carrying I1 at an angle 0 degree. Both are carrying same phase current. I'm not going with the derivation. I'm not going with the derivation. Kindly observe it. First, for A1 conductor, we will write the GMR. Then for A2 conductor, we will write the GMR. Then we will take geometric mean of these two to get the GMR of the phase A. Okay, so GMR of phase conductor A1. GMR of the subconductor A1. Very simple. What is self of A1? See, one thing, listen. One thing I have to explain here, just listen. We have two conductors, one beside the other. A1, A2. A1, A2. Two conductors, one beside the other. Conductor A1 is carrying some current. Conductor A2 also carrying some current. A1 will have its own self-magnetic flux linkages. A1 will have its own self-magnetic flux linkages. A2 also will have its own self-magnetic flux linkages. Okay. Between A1 and A2, we have mutual linkage also. Conductor A1 will have self-linkages. Conductor A2 will have self-linkages. Between A1 and A2, we have some mutual linkages. Now, the question what I am asking here is, whatever the mutual linkages we have between A1 and A2, whatever the mutual linkages we have between A1 and A2, can we consider these mutual linkages as a part of self linkages of the phase A? Self linkages of the phase A. A1 will have self linkages, I am saying. Conductor A1 will have self linkages. Conductor A2 will have some self linkages. Between A1 and A2, we have mutual linkages also. Whatever the mutual linkages we have between A1 and A2, can we consider these mutual linkages as a part of phase A self linkages? Phase A self linkages. Because whatever the mutual you are saying between A1 and A2, occurring within the phase A, right? Occurring within the phase A. So those are considered to be self linkages of the phase A itself, even though you are saying a term like mutual. I don't know whether you have understood this or not. Please kindly confirm once. All of you have understood this? I'm writing the statement, right? The mutual linkages occurring between A1 and A2 conductors. A1 and A2 conductors will be a part of self linkages of phase A. Self linkages of phase A. Getting? Self linkages of phase A. So whatever the distance S we have now, that will be a part of GMR of the phase A. Whatever the S we have, that will be a part of GMR of the phase A. And you see, Whatever the D we have capital D, that will be the mutual distance between phase A and phase B. Mutual distance between phase A and phase B. Okay, so this D will come in the GMD, so called the mutual distance calculation. So if you want to write GMR of the A1 conductor or self distance of A1 conductor, GMR of A1 conductor, or you can say self distance of A1 conductor, first I should consider, listen please. First I should consider self distance of A1. In how much distance we get the self linkages of A1? R1 dash, 0.7788 into R1. R1 dash. Okay, next. Between A1 and A2, we have a mutual. In how much distance we get the mutual linkages? Yes. That also we have to consider in the GMR calculation only, because that is a part of the self linkages. So I can say multiplied with yes. Kindly follow it. I am not discussing any derivation. Just look here. How many terms we had now? 2 terms. R1 dash, yes, 2 terms. So we have to take geometric mean of these two, means square root of R1 dash. Yes, that is GMR of the subconductor A1. GMR of the subconductor A1. Similarly, you write here if you want. So R1 dash is self of A1. Self of A1. S is mutual between A1 and A2. A1 and A2. Mutual between A1 and A2. Next, GMR of conductor A2. GMR of the conductor A2. First to take self of A2. What is self of A2? R1 dash. Self of A2 is R1 dash. Between A2 and A1, we have a mutual. In how much distance we have that mutual? Yes, that also to be taken into the self linkages of phase A. Okay, so how many terms you have? 2 terms, and you'll say it is square root. So this is self of A2, and this is mutual between A2 and A1. Mutual between A2 and A1. Okay. So after getting this GMR A1 and GMR A2, yeah, already I said S is very, very high compared to R1. So no need to bother, is it S plus R1 or S minus R1. Okay, you take it S only. That's why I made that practical things earlier. Next, let's continue. So after considering this GMR A1, GMR A2, if you take up GMR of the whole phase A, that will be geometric mean of these two. So come to be GMR of the overall phase A, nothing but GMR of the subconductor A1 multiplied with GMR of subconductor A2 under square root of GMR A1 into GMR A2. But you know already both GMRs are equal. GMR A1, GMR A2 both are equal. Of course, you will get the same one. So it is root of R1 dash into S multiplied with root of R1 dash into S, right? So it will come to be square root of R1 dash into S. That is nothing but GMR of any one of the subconductor. GMR of any one of the subconductor. GMR of any one of the subconductor. Done. What about GMR of the phase B? Is it looking same as phase A? Yes, because sizes of the conductors are same, spacing is also equal. So GMR of phase B will be coming same as GMR of phase A. And similarly, GMR of the phase C. Means my interest is to tell you, if the subconductor configurations in each and every phase are identical, then GMRs of all the 3 phases will be equal. Okay, let me write it. If subconductor configurations in all the 3 phases are equal, are equal, then GMR of phase A, phase B, phase C, all the three are equal, then you can say sometimes as GMR of system or simply GMR, doesn't matter. GMR of system is nothing but geometric mean of the three phases GMRs. GMR of the system you write, L simply GMR also, no issue. It will be the geometric mean of the three GMRs you have, phase A, phase B, phase C, and all the three are equal in the sense it will be simply GMR of any one of the phase. GMR of any one of the phase. Right now it is the root of R1 dash into root of R1 dash into S. Okay, done. Next, let's continue. See, for example, if you have three subconductors, let us say, for example, if you have three subconductors, then how will be the GMR? Rather than two, if you have three subconductors, then how is the GMR? At that time, we have to calculate GMR of A1, A2, A3. Geometric mean of these three will give GMR of the phase, GMR of that particular phase. Similarly, if you have four subconductors also. Okay, so we'll take up those things in problems. First of all, I want to make a comparison. Between three-phase single conductor system and three-phase bundle. I will discuss about three subconductor system, four subconductor system later. For time being, what I want to make here is a comparison between three-phase single conductor system and bundle conductor system. Just look here. I have three-phase single conductor system on one side. Single conductor system on one side. Okay. So on the other side, I will be taking up three-phase bundle conductor system. Three-phase bundle conductor system. Bundle conductor system. Okay. Kindly observe. So I'm showing three-phase single conductor system first. It's a phase A conductor, and it's a phase B, and it is phase C. All the three are of equal size. Okay. Phase A, phase B, phase C. Each one will have a radius of R. Distance between phase A and phase B, X. Between B and C, it is Y. Between C and A, it is Z. Okay, for your understanding, I am giving the radius of each subconductor 4 centimeters. Radius of each subconductor is 4 centimeters in the single conductor system. Now, observe here, same system as it is, I am replacing in the bundle with a small change. I'll tell you. Change exactly. Same system we are repeating now. But in place of phase A, I will be keeping two subconductors, namely A1, A2. A1, A2. In place of phase B, I am keeping two subconductors, namely B1, B2. In place of C, I will be keeping two conductors here, namely C1, C2. A1, A2, B1, B2, C1, C2. Next, radius of each subconductor is R1. Radius of each subconductor is R1. Can you please tell me what is that R1 value? Can you please tell me what is that R1 value here? Yeah. Anybody please? What's that R1? R1 value will be equals to R by root 2, na? R1 is nothing but R by root 2. R by root 2 in the sense R value 4 centimeter and it will be 4 by root 2. How many centimeters? 4 by root 2 means? Tell me the number. 2.8 number 2.8 to 8, I think. 2.8 to 8 centimeters is the radius of each subconductor. XYZ distances will be as it is. XYZ numbers will be as it is. But here A1 to A2 spacing how much? What is the spacing between A1 and A2? That we don't know. Assume that they have given in the data. Assume that this S value was given in the data. S value was given in the data. I am saying it is 30 centimeters. In bracket, I am saying it is given in the data. 30 centimeters that they have given in the data. Okay. Tell me please. In the single conductor system, just listen, concentrate. Single conductor system. What is GMR? What is GMR of the single conductor system? It is simply 0.7788 into radius of the conductor. 0.7788 into radius of the conductor. How much is this number? Anybody? How much is this number? Please tell me. Yeah, 0.7788 into radius. Anybody? Nobody is saying. 3.115. 3.115 centimeters. Okay, good. What is GMD here? GMD. Did he mention anything about transposition? Did he mention anything about transposition? No. If he didn't mention it, we have to assume that it is transposed. After doing transposition, what is GMD? It will be cube root XYZ. Cube root of XYZ. DAB, DBC, DCA. Okay, done. Next, please tell me, what is GMR of this system? See, observe, phase A, phase B, phase C, all the three are identical. Phase A, phase B, phase C, all the three are identical. GMR is nothing but GMR of phase A itself. In case of bundle, I am writing in case of bundle in the next slide. For bundle, GMR is nothing but GMR of the phase A. GMR of phase A. What is GMR of phase A? What is GMR of phase A? Just now we said, it is root of R1 dash into S. R1 dash into S, we should say. So it will be square root of R1 dash 0.7788 into R1 into S value. So you can get from this like square root 0.7788. And what's the radius R1? 2.828. And how much is the value of S? 30. Okay, please tell me this number how much? How much is this GMR value? Calculate it and tell me. Calculate this number and tell me. 8.128? Good. 129. 8.129 centimeters is the GMR of the bundle. Okay. What is GMD of the bundle? GMD. Is it same? Can we say? GMD? See, already I made a statement that the spacing between subconductors, yes. It is negligibly small compared to XYZ numbers, right? S is negligibly small compared to XYZ numbers. So definitely I can say that phase A, phase B, phase C positions will be more or less same. A, B, C positions will be more or less same. So XYZ values will be as it is compared to previous numbers. So in that perspective, GMD will be coming like cube root of X, Y, Z. Okay, by neglecting spacing between subconductors. By neglecting S value, spacing between subconductors. By neglecting the S value. Now, a small comparison we want to make between these two, as I said to you earlier. GMR, other name is self-GMD. Other name is self-GMD. GMR. How is the GMR of bundle compared to single conductor system? GMR of the bundle conductor system is greater compared to single conductor system. That is one observation to be noted. 8.129 here. but in the previous it is 3.115. So comparative statement here, GMR of bundle conductor system will be greater compared to GMR of its equivalent single conductor system. GMR of its equivalent single conductor system. But how are the GMDs we are getting? How are these GMDs? Yeah, how are the GMDs? GMDs are equal, right? Approximately. So you write GMD of bundle conductor system. GMD of bundle conductor system will be approximately equal to GMD of its equivalent single conductor system. GMD of its equivalent single conductor system. Okay, see, already we mentioned various names. GMR can be called as self distance, or you can say it as self GMD. Self GMD. And the GMD can be called as mutual distance, or you can name this as mutual GMD. Mutual GMD. So this is one of the important point to be observed. One of the important point to be observed. So I'm sorry, there was a network issue. Okay. Yeah. So let's continue. Let's continue with this. So is a single conductor system is also practical only. Single conductor system means each and every phase is consisting of one conductor. Single conductor system means each and every phase is consisting of one conductor. Okay, see, on the basis of this slide, we are going to write the advantages of using bundle conductor system compared to single conductor system quickly. Okay, so I'll say advantages of bundle conductor system compared to the three-phase single conductor system. Compared to the three-phase single conductor system. Okay, can you observe now? First advantage. Already we said electric field intensity is reducing, corona is reducing, so power loss reduces. Electric field intensity reduces, corona is reducing, so power loss reduces. That's one. Second one, you see, inductance. L per phase formula is 0.2 natural logarithm GMD by GMR in terms of millihenry by kilometers. Okay, so see this inductance formula 0.2 ln of GMD by GMR. It is valid for single conductor system, bundle conductor system, or any system. Simply you can write this formula 0.2 ln of GMD by GMR. Okay, now you see, if you take up this comparison, GMR of bundle system is more compared to single. So obviously you can say GMR is high, but GMD remains same. Because of this value will fall down and inductance value decreases. Okay. Because of this decrement, you know, reactance per phase reduces. Voltage drop in the system reduces. Right? And you know, maximum power transfer capacity, P maximum. Let's look at this term. Maximum power transfer capacity, P max. Maximum power transfer capacity. P max. Already we know this equation, right? Mod Vs into mod Vr by X. So as X value was falling down, P max value will increase. So obviously system stability is going to be increased. Stability of the system increases. Okay, this is the second advantage. Inductance decreases if you are using bundle conductor system. So voltage drop is decreasing, maximum power transfer capacity is going to be increased. Okay, next, third one. I'm going to say with respect to capacitance calculation here. Area, we have not done the capacitance calculation till now, but still I will give the equation for the comparison. I will derive that equation later. Okay. So first I will say capacitance per phase equation 2 pi epsilon naught epsilon r by natural logarithm GMD by GMR will not come here. GMR will not come. It will be simply radius of the conductor. GMR will not come. It will be simply radius of the conductor. Okay, power loss decreases. See, this is in farad by meter, and moreover, this is for three-phase single conductor system only. Means if you have only one conductor in each and every phase, that conductor radius we are going to dump here. Okay, this is for three-phase single conductor system. Capacitance per phase. And if it's a bundle conductor system, how it is? This equation, how it is going to be modified? Means C per phase will be coming like 2 pi epsilon naught epsilon r by natural logarithm. Numerator as it is GMD only, but in the denominator we are going to get a term like DS. It's not GMR, it's not GMR. DS, I will tell you. It's a very simple calculation, very simple calculation. This is in farad by meter. This is for three-phase bundle conductor system. Bundle conductor system. See, in some textbooks, the people will say GMRL, GMRC also. GMRL for inductance calculation, GMRC for capacitance calculation. Only one change is that while you are calculating DS, DS will be similar to GMR only. DS calculation will be similar to GMR, but only one change is that you don't get the 0.7788 factor of multiplication. You don't get the 0.7788 factor of multiplication. So it will be simply root of R1 into S. That's the change. Root of R1 into S. That's the change. So anyhow, whatever it is, this DS value definitely increases. DS value definitely increases. And ln of this number reduces and capacitance value increases. Capacitance value increases. Means if you are converting a three-phase single conductor system to bundle, capacitance value increases. Because of this increment, charging current per phase increases. Charging current per phase increases. Okay, so reactive power delivered by the transmission line increases. Q delivered by line increases. Okay, and power factor of system also going to be improved. Power factor of system increases. Power factor of system also going to be increased. Okay, we have some more advantages of bundle conductor system that we'll discuss tomorrow. Only we discussed about L and C. L and C, how these values are going to be changed from single conductor system to bundle. Few more advantages we'll discuss about it. Okay, so if you have any doubts, you can raise your hands. Class is over by this point. Class is over by this point. I'll make all the hands go. Kindly raise your hands if you have any doubts. Vishnu Ajit.
Hello, sir.
Tell me, Vishnu.
Sir, my doubt is regarding corona, sir.
Okay.
Sir, you did mention that in order to reduce corona, we use bundle conductors.
Yeah.
And mainly, this corona occurs due to this high electric field intensity.
High electric field intensity, yes.
Sir, usually when we build a transmission line, usually the metallic part is surrounded by the insulator, no, sir?
No. Power conductor you are saying me?
Yes, sir.
Power conductor is not surrounded by insulator anywhere. It's a just open conductor.
So just a metallic and plastic sheet.
Just a metal, that's it. There is no insulation on the surface of overhead line.
Sir, so when an electric field is formed, the charges will be surrounding that entire metal.
Yes.
So rather than using these bundle conductors, if I just connect a wire that is connecting this this conductor, this sheet, and directly to the tower, within this all charges get grounded and corona will be zero.
Then you will get a short circuit fault.
Oh, since the entire line is exposed directly.
Directly to ground means it's a fault, right?
Yes, sir. Oh, so this, like what I actually meant was, if you look at the lines, sir, here, they're looking like blackish. So that thing isn't insulator or
where you have seen it?
Like normally near our houses, there you'll have some towers there.
That's a cable.
That cables, those
That's
cables.
I'm not discussing about it. I'm discussing about overhead lines of 130 kV, 33 kV, 11 kV lines.
So those will be pure just metallic things.
Just metal. Whatever the white color you see, it's aluminum metal, right?
Oh, okay. So that is different from the conductors that we see outside our homes.
Inside your house as well as outside your house, whatever the conductors you will draw, those are insulated cables. Unarmored insulated cables, PVC insulated cables, service main wire and all.
Okay, sir.
Okay, the people, the distribution, overhead distribution lines, overhead transmission lines, these are not insulated conductors.
So that's why we are talking about these faults.
Faults.
Okay. So thank you, sir.
Okay. Yeah.
Good morning, sir.
Good morning. Yeah, tell me.
Sir, bundle conductor used only for the 220 kV above line only, no, sir?
Above, yes.
Or else we use for the
Not
130
for
kV.
220 kV. Not for 220 kV. Above 220 kV is 400 kV, 75 kV only. Then
From
only it is economic.
From
Then
400
only it is
kV we are
economic.
using.
For 220 kV also we don't use because of its high cost in insulation.
Okay, sir. Sir,
Mhm.
GMR calculation is the practical application is the face-to-face clearance for finding, is there?
GMR?
Sir, GMD calculation is there, sir, for finding the GMD. In the practical data sheet, we are saying the face-to-face ground clearance are there, no, sir?
Yes.
From that only we are getting that
From that
value
only we are going to calculate GMD. Yes.
6.1, 7.1. That.
Yes.
Okay, sir.
The ground clearance is different. Ground clearance is different. Face-to-face clearance is there, na?
Yes, sir.
Face-to-face clearance. Based on that, we'll calculate GMD.
Okay, sir. Sir,
okay.
Okay. Sir, there is a in the power conductors we are using the metallic insulator. Is there, no, sir? Metallic sheet.
Metallic
for
sheet.
No. For the
Bundle.
Yes, sir. In the bundle conductors, we are using the
metallic link we are using.
Sir, I saw in our nearby home there is a 3 lines only. Means it's a single phase only. They are using the some silver wire is connected in between 3 wires. Is also same.
It's
that
not
one, sir?
silver. That's insulator. It may be in the distribution line. Whichever that separator you are seeing, that's the insulator.
Okay, sir.
For example, you see outside distribution lines, 3-phase lines.
Yes, sir.
If that space is very less, to maintain gap between the phase conductors, they will keep this PVC insulator.
Okay, means it's a ring
Just
type,
like a pipe material.
Okay.
PVC material.
Okay.
It's an insulator. It's an insulator.
Okay, sir. It's only, sir.
Yeah.
Thank you, sir.
Ramakrishna.
Hello, good morning, sir.
Good morning, Ramakrishna. Tell me.
Sir, is there any possibility that the distances between conductors would be given in vectors and a problem is given on that? We have to take magnitude and solve or directly vectors, sir?
You have to take only magnitudes.
Okay, sir. Directly
Are you thinking about the previous gate problem electrical intensity calculation?
No, sir, I didn't see it yet, but I just got it out.
No. Not vectors. You have to go with only physical distance, magnitudes.
Okay.
Vectors we will take while we are thinking about field intensity.
Okay, sir.
Because it's having direction also. Not only magnitude, it's having direction also. At that point, if it is needed, we have to go with the direction.
Yes, sir. Okay.
Okay.
Yes, sir. And another doubt. For high voltages, there is an extra loss for corona. No? So why do you go for high voltages then?
For bulk power transmission as well as to have good stability.
But we are getting extra loss term, no, sir. So it doesn't matter. By using bundle conductors, we are reducing.
How many? So for example, if you want to transmit 1000 megawatt power,
okay, sir.
How many 130 kV lines you run?
Oh yes, many. Yes.
Rather than that, one 400 kV line might carry the whole power. 400 kV double circuit or 75 kV double circuit.
By using bundle conductors, we decrease that.
Cost of the system will be heavily decreased compared to that many number of circuits.
Okay, sir.
Okay.
Yes, sir. Sir, and power system protection will be taught by any afterwards, no, sir, or after this subject or on a different time?
Please contact
Okay. It doesn't come in this transmission distribution.
No. Whatever the topics I have written, that I will discuss.
Okay, sir. Okay. Thank you, sir.
Sachin.
Sir, my doubt is regarding day before yesterday. It means you say now in skin effect consider the inductance value is maximum. It means internal psi internal is 0 na. In that inductance expression,
It will be only external term.
yeah, but in that expression mu 0 by 2 pi ln of d by it's r1 or r1 dash.
Are you writing external separately, internal separately?
No. But you said na only it is depend on external. So in that expression, in that
You have only external means only R1, right? You don't get R1 dash.
okay, yeah. That
Already
means-
internal. After adding internal term to external, you will get R1 dash.
okay.
If you don't have it, you have to consider only external. That's it.
That means it may be only R1.
What is the external inductance formula?
Mu 0 by 2 pi ln of d by R1 dash.
That is total inductance, not external. Internal plus external is the formula.
External mu 0.
After adding internal term only, you will get that R1 dash.
Okay. External mu 0 mu r by 2 pi ln d minus r2 by r1.
D minus R2 by R1. Okay, D minus R2 is approximated to D.
Okay.
D by R1. That's it.
Okay. Thank you, sir. Sir, and how to join this Telegram group doubt session?
You just put a message to me in the Telegram.
Sir, I don't have link.
You number. I will give my mobile number.
Okay.
96184619118. Okay.
Okay. Thank you, sir.
Pallavi.
Sir, can you please explain once shortly the why the electric field intensity inside the conductor is 0 and on the surface is maximum?
See, what is the other name for electric field intensity we mentioned? Voltage gradient.
Voltage, yes.
See, if you are
Voltage
applying a voltage V, to this conductor, at all the places inside the conductor, voltage will be remain same at V.
Yes, sir.
Because you are applying a voltage V, to a conductor means at all the places we have a voltage of V only.
Yes.
Okay, now voltage gradient means what? Change in the voltage with respect to distance.
Distance, yes.
So if you are moving from one point to other point inside the conductor, do you have any change in the voltage?
No, sir, it's same.
Then gradient is 0 inside the conductor.
Okay. And on
the surface of conductor, we have a voltage V.
Yes, some is
On
changed.
the surface of conductor, we have a voltage V. If you are moving from conductor surface to outside, there is no excitation, right?
Yes.
As you don't have any excitation, obviously I can say from surface of conductor to out, there is a change in the voltage, definitely.
Yes.
So definitely
That's
there is a
right,
field
yes.
intensity existing on the surface, and it will be the maximum value compared to any other place.
Okay, sir. Thank you, sir.
Okay.
Yes.
Yeah. Allah Naveen Sai.
Sir, good morning, sir.
Good morning, Naveen.
Sir, in economical connections in transmission system, that is for step up, you said delta star grounded, and for step down star delta, no, sir. But in generation, for step up, the alternator is connected in star grounded system, no, sir. Then how it is economical again?
The alternator we are connecting in star grounding for different view. Rather than in delta, why you are going for star grounded means to provide a return path current, neutral current.
Yes, sir.
One thing. And to overcome the issues of line to ground fault current circulation and all.
Yes, sir.
That's why have you attended FNS?
Yes, sir.
Then you might be knowing it. For example, if you connect your alternator in a delta, let us say like this. Okay, alternator in delta,
Okay.
then you don't have an axis of neutral wire, right?
Yes, sir.
And you don't have a phenomenon of neutral grounding or anything.
Yes, sir.
But unfortunately, if you have a single line to ground fault at the terminals of the alternator,
It will be huge current.
there's no current.
Okay. In delta connection.
There is no current at all. And not only that, we don't have any current, and remaining phase voltages will be rising to their line-to-line values.
Yes, sir. Again, that will be
That we discussed.
isolated neutral condition.
It will be like isolated neutral connection. Then that will be leading to the insulation flashover of the insulators connected between this phase to ground in the tower.
Yes, sir.
Okay, so that's a problem. So to overcome this, we have to provide a better neutral path, so that we have to go for only star grounded alternators practically.
Yes, sir. That
Okay,
means at
now
every
next.
generating station, we have this configuration, star configuration, sir.
Again, you are saying star. What is the star? You have asked me
I
a
mean,
doubt about generator, right?
Yes, sir. I mean, step up we can see, we can find only at generating stations, sir, mostly.
See, one thing, Naveen, whether your generator is a delta generator or star generator, doesn't matter to me, na? Only 3 wires will come out from generator, right?
Yes, sir.
Because you have already connected your neutral wire to ground.
Yes, sir.
So whatever the 3 phase wires you are getting now, this you can connect either to a delta or to a star. That's your wish.
Okay, sir.
Understanding? See, if it's a star, if it's a delta, you have 3
sir.
wires outcoming, and you will be joining them. And if it's a star, then also you have 3 wires outgoing, and this neutral is connected to ground.
Okay,
So
sir.
we are operating our system with only 3 wires. There is no neutral wire at all. But wherever you have a star, that neutral point is connected to ground. That's the thing what you're doing for connectivity.
Okay.
Okay. So as you have only
Yes.
3 wires, you no need to bother. The star is connected to delta, delta is connected to star. You not at all required to think about it.
Okay.
Okay. So a star connected alternator,
Okay,
3 wires are coming out. These 3 can be given as an input for delta winding. Okay.
Yes, sir.
I don't know whether you are understanding or not. Please ask me clearly what's your doubt.
Understood, sir. Now
Naveen.
got it.
Tell me.
Now got it,
if you
sir.
have any
Understood,
doubts. Clear?
Clear, sir. Thank you.
Okay, fine. Any other doubt you have, Naveen?
No, sir.
Salman.
No, sir. Clear.
Okay. Salman.
Good morning, sir.
Good morning, Salman. Tell me.
Sir, we use the metallic spacer, right, sir, between the bundle
Hmm.
conductor.
Hmm.
Can we say that there is no current flowing through that link, sir?
Yes.
Because all the potentials are same.
Approximately. No current flow.
Okay, sir. That's all, sir. Thank you.
Okay.
Hello, sir.
Tell me, Akshay.
Sir, my doubt is regarding corona in the bundle conductor system. Like, suppose, for example, we have one single conductor, and instead of that, we are using 2 subconductors.
Okay.
So, in the 2 subconductors region, like in the center between them, due to the first conductor, it will experience some electric field intensity, and due to the second conductor also it will experience
So that
some.
depends upon the directions also.
Okay.
Is A1 conductor you take, and it's a A2 conductor.
Yeah. And at
Okay.
the center,
So you
like
assume it's a plus Q charge.
Okay.
It is a plus Q by 2 charge, and this will be plus Q by 2 again.
Okay.
So if it's a plus Q charge, positive charge, how will be the electric flux lines? How will be the electric flux lines if it's a positive charge leaving out?
Okay. Yes, sir.
If it's a positive charge, electric flux lines will be radially outward from the charge.
Outwards. Yeah, correct.
So I will be having the flux line something like this. Okay.
Okay.
And similarly, A2 is also positive. So your flux lines will be in this manner.
Okay.
Now, if these two charges you make it closer,
Okay.
then what will happen? Whatever the flux line coming here and these two will be opposing, right?
Okay. Yeah.
As these two are opposing, it will bend like this.
Oh, okay.
Okay, so at the middle, you don't have any electric flux.
Okay, sir. So
And
whatever
all
that
these lines, whatever we have, it will be bended in this manner, bended in this way. So high concentration you will have at this place.
Oh, okay.
And similarly,
that,
all these lines are bended like this, and high concentration will be at this place.
sir, that will that high concentration value be equal to the one we calculated right now?
Ah, yes.
Okay, sir.
That is effect of both A1 plus A2.
Okay, sir. Got it. Got it. Thank you, sir.
Ashwin Prasad.
Hello, sir.
Tell me, Ashwin.
Good morning, sir. Sir, that derivation 63F. Corona.
Okay. Tell me.
Sir, in this, both the polarity of the conductors are same, right? So, sir, in the derivation, one field should be opposing the other, right?
That's what I explained just now. I am calculating field intensity at this place.
Okay.
At this place, I am calculating field intensity. I am calculating field intensity at this place.
Okay, sir.
So A1 will be in this direction. A1. How will be the A2 flux? It will be in the same direction, right?
Okay, okay.
At this place. At this place, it is opposing.
Okay.
At this place, it is same, right? Aiding.
Yeah, at that case, it's same.
This is 1, this is 2. Which point is higher field intensity, you can say? 0.1 or 0.2?
0.1.
So we have to take that as a highest field intensity at any point.
Okay, okay.
So it will be addition of both.
Okay, so we don't need to calculate on the lowest point.
No, not needed, right?
Obviously, the field will be
Whichever
reduced.
is highest, that we have to consider, based on which the corona is going to happen.
Okay, sir. Okay, sir. Thank you.
Okay. So any more doubts you have? Please raise your hands. Any more doubts you have? Please raise your hands. Any more doubts? Please kindly raise your hands. Gopi.
Hello.
Tell me, Gopi.
Yes, sir. How corona will impact on a radio interference, sir?
Hey, corona discharge is a high frequency discharge.
Sir, how you can find it will have a high frequency? Actual operating voltage is at 50 hertz.
It is delivering light as well as it is delivering sound, na?
Yes, sir.
Light is a very high frequency discharge only, right?
Yes, sir.
That glow what you are getting, the radiation what you are getting there, that is of high frequency.
Okay,
that high frequency discharge might disturb the communication signal.
Okay, okay. Sir, if you want to disturb any signal, whatever the signal which we are disturbing, that will contain more or less equals to frequency, but the surrounding frequencies, signal frequencies are in the order of megahertz or kilohertz.
Yeah. See, whenever the discharge frequency, what you are saying, corona discharge frequency, matches with the communication signal frequency.
Okay.
Then it will create a distortion.
Okay. But how much it will impact that we don't know, sir, or it can be solved by mathematics?
We don't know exactly. We don't know because how that wireless communication signals are flowing, we don't know, right?
Okay, sir. In practical, I observed on parallel transmission lines, communication lines also carried in
where?
Is it communication lines,
Where?
practical communication lines.
Where you have seen?
That means okay, near to Visakhapatnam, it's long transmission lines. I observed.
Just you take a snapshot and send to me. I'll tell you whether those are communication lines or any other lines.
Okay, sir.
Okay, if there are communication lines like that, then there's a radio interference and communication lines.
Okay, sir.
Okay, Gopi, please send to me. Please send to me that pic. That will be helpful to our lecture also.
Okay, sir.
Okay.
If it
Possible,
is not,
take a video also. Take a video and send.
Exactly, I don't know, but I figure out that.
No problem. Whichever you see that you send to me, I will tell you whether those lines are communication lines or any other lines. If those are communication lines, we will discuss about it.
Okay, sir.
Okay.
Okay.
That's it,
Thank
Gopi. Any other doubts you have?
Sir, actually in textbooks, corona disruptive voltage term, I read it.
Are you belongs to IES batch or GATE?
Sir, IES batch, sir.
IES, I will discuss corona separately. Disruptive voltage, visual critical disruptive voltage, all these things I will discuss.
And that means completing overall T&D after ESC topics discussion, sir.
No, maybe at the end of this T&D itself, I will continue with the ESC topics if possible.
Okay, sir.
A daily 2 hours I will take. I will be completing those IES topics also.
Okay, sir.
Okay.
Okay, sir.
Any
Thank
other
you, sir.
doubt you have, Gopi?
No, sir. Clarified.
Jessica.
Sir,
Tell me, Jessica.
sir, I had a doubt in the last part that capacitance, per phase capacitance, how it is varying when we use bundled capacitor. Sorry, bundled conductor.
The DS value you calculate, Jessica, for this problem. Here. This problem you take and you calculate radius is 4 centimeters already in this one. And what is the DS for capacitance calculation? Root of R1 into S, right? So same calculation as this one, but you don't get 0.7788.
Okay, sir.
Getting me? So it will be root of 2.828. I'll write here DS. Capacitance calculation. So it will be root of R1 into S. So it will be root of 2.828 into 30. Tell me how much is this number?
$9.21, sir.
Which is higher than the radius of single conductor, right?
Yes, sir.
That's what I have mentioned in the advantage.
Okay. Sir. Got it.
That's what I said.
It's sir. Okay, sir. Thank you, sir.
Any other doubts? Please raise your hands. Any other doubts? Navdeep.
Hello, sir.
Tell me, Navdeep.
Sir, why you have taken charge distribution equal if sizes, radius are different, sir?
Sizes are equal only, I said later on, right?
Okay, sir.
Okay.
Okay.
But as a definition, most of the times we are going for bundle conductor. We used to consider the size of each and every subconductor as equal.
Okay. Sir.
Okay.
Okay. Sir.
That's it. Any other doubt you have?
No, sir.
Okay. Anil Kumar.
Sir, good morning, sir.
Good morning, Anil. Tell me.
Sir, you told that the conductor can be arranged in different manners, sir. Diagram, that RYB. Arranging that sequence or alternate, sir.
No, alternator might be giving RYB, but they have changed the transmission line, that sequence. But there is no issue with that.
Okay, sir. Okay.
Nothing change.
Okay, sir.
Ultimately, their intention is while you are reaching to the grid, be clear which is a R phase and which is a Y phase, which is a B phase.
Okay, sir. Okay.
Because in that grid, many other systems are getting interconnected, right?
Okay, sir.
Yes or no? So to whatever the incoming line we have, that phase sequence should be synchronized with the other phase sequences.
Yes, sir.
For that purpose, they will give that indication on the tower.
Okay. Sir, how to identify whether which conductor is top and which conductor is bottom?
Just by height, they will give that RYV in a sequence on the tower. For example, I have shown here. They have given like this, na?
Yes, sir.
Which looks to be top for you among these three?
Sir, yellow, Y phase.
This is top, right? B.
Okay, sir. Okay.
Height wise.
Sir,
Height.
okay,
Height wise B. Next R. Next Y.
Okay, sir.
Okay.
Okay, sir.
Any other doubt you have, Anil Kumar?
No, sir. Thank you, sir.
Okay. Anybody have doubts? Please raise your hands. Gauri Priya. Gauri Priya Ramesh.
Hello, sir.
Tell me.
Why, sir, corona is more in rainy season?
Because of low temperatures. See, actually, dielectric strength of air depends upon temperature and pressure.
Yes, sir.
We will say it is 30 kV by centimeter under healthy conditions, under fair weather conditions. But if temperature and pressure are getting changed, obviously dielectric strength of air also going to be changed.
Yes, sir.
Because of that, obviously corona possibility will be more in the rainy season because dielectric strength may decrease in the rainy season and the winter seasons.
Okay, sir. Thank you.
Okay.
Okay, sir. Thank you.
Any other doubts? You can raise your hands. Anybody having doubts? Please raise your hands. Gopi, tell me, Gopi.
Yes, sir. At the starting of T&D, discussion about the skin effect, sir. I have one doubt.
Tell me.
Explaining internal inside of the conductor current is minimum at the at lower point inside the conductor. I know that Lenzley applicable applied for first quarter cycle of sinusoid voltage accepted one, sir. After quarter cycle of the positive half cycle of sinusoidal, it is not the correct one.
Original current also changes, right?
Yeah, yes, sir.
Original current also going to be changed according to the quarter cycles. What you are saying?
Oh, yes, sir. From 90 degree to 180 degree, the magnitude of the current will be decreases, but according to the Lenz law, it opposes the cause to oppose this cause. Whatever the magnitude at high at first quarter cycles, it should maintain up to 180 degrees. That means it must be adding to the from
that addition portion is very less.
Okay. అంటే in
The condition
transformers,
portion is very less. Most of the times it will be in the opposing mode only.
that means, sir, in transformers, Murali Krishna sir said about
Ah,
this.
okay.
and
Okay, okay. That's okay. That's okay.
That means
I do accept. No, I do accept with that. But here we are thinking about only current opposition.
Okay, okay.
Current opposition, how much we have?
That means, my question is about the.
See, simply whatever the flux to be produced by the eddy current,
Okay.
it should oppose the actual flux.
Okay.
Whatever the flux produced by eddy current, it should oppose it. In that way, we should show the direction of current.
Okay, that is
Whether the
valid
current is
only.
increasing, decreasing, that's okay.
Okay. But then
You have
only
already listen. You have already that flux phi, right?
Okay.
Now you have eddy current.
Okay.
You show the eddy current direction. You show the flux due to eddy current. Is it opposing that phi or supporting that phi?
Opposing or it is adding, it will depends on the magnitude of original flux, sir.
That's okay. That you are saying about the sinusoid. I'm saying with respect to right hand thumb rule.
Okay.
Is it opposing the phi or supporting the phi?
Okay, opposing, but I accept
only.
that only up to quarter cycles. After quarter cycle, it is adding in my point of view. That is.
Then your original flux will change. Original current will change. After that quarter cycle, what you are saying, your original current and original flux is also changing, right?
We are assuming that first it is cross. That means it will continue up to 180 degree.
180 degree, yes.
Okay, from 90 degree to 180 degree, original flux in the same direction. But to affect this cause, from Lenzler, current flux should be added.
One thing, listen. See, EMF is in lagging by an angle of 90 degree with respect to flux.
Okay.
Okay. Then your current will be again 90 degree lagging with respect to EMF.
Okay.
Then current will be 180 degree opposite to the flux, right?
Okay.
Original flux, what it is getting created. Then obviously, if one is in one direction, other one will be in opposite direction.
From phasor diagram representation.
Yes. Yeah.
Okay.
Okay.
Okay, sir. Okay, sir.
Yeah. So any other doubts? Any other doubts? Please raise your hands. Okay, I think nobody's having a doubt. Closing the session. Thank you.